Okay, so the next chapter, chapter 5, induction and recursion. 5.1, mathematical induction. So what is mathematical induction? So mathematical induction is a method of proof in mathematics used to prove a statement P of n, a statement of the form P of n, where n is a natural number. So please remember that previously we said beginning of the semester, when we talked about propositions, we saw that some propositions could depend on a variable, let's say n or x, and the truth of those propositions also depend on the value of the variable. So let's consider proposition of the form P of n, or a statement of the form P of n. And if we want to prove that this is true for every n in n, so every natural number, then we can use a method called mathematical induction. So let's see what we do in this method. So in this method, to prove P of n for every n. So number one, first, we check that a P of n holds for n equals 1. So this is called basis step. Basis step. And second, then next, we assume that P of n holds for n equals k, and we prove that it holds for n equals k plus 1. This is called inductive step. Okay, so when you combine these two together, then mathematical induction says that P of n will hold for every value of n. Let's see why. So first of all, P of n, we check that P of n holds for n equals 1, so we just check it separately. But we want to show that P of n holds for every natural number n. So far, we just check that it holds for n equals 1. What about n equals 2? Now, once we prove the second step, which is called inductive step, which says that if P of n holds for n equals k, then it will hold for n equals k plus 1. Once we complete this step, because we already have checked that the P of n holds for n equals 1, right? So if you set k to be 1, so this inductive step says that once you know that it's true for n equals 1, then it will be true for n equals 1 plus 1, which means it will be true for n equals 2. And once you check it for n equals 2, again, the second step will imply that, inductive step says that because it's true for n equals 2, therefore it must be true for n equals 2 plus 1, which means it must be true for n equals 3. And you can continue this process forever. So once it's true for n equals 3, it will be true for n equals 3 plus 1, which is 4. And then it will be true for n equals 5, and so on. So it will be true for every, so that's why the principle of mathematical induction says that once you complete these two steps, we can conclude that P of n holds for every natural number n. So let's look at an example. Show that 1 plus 2 plus 3 plus plus n equals n times n plus 1 over 2. So this is, I think, the most famous and most standard example of mathematical induction. And it's a very famous formula, the sum of the first n integers, 1 plus 2 plus 3 plus all the way to n, is equal to n times n plus 1 over 2. So please remember that we had different methods of proof in mathematics. But if you want to use the mathematical induction method, the very first thing that you have to be sure of is that you have to have a statement that is supposed to be true for every natural number n. So there must be, you must have a statement of the form P of n, a statement that is supposed to be true for every natural number, not every real number, for example. And here n is a natural number, so that this is true for every n in n. So this requirement is met. And once we are sure about this fact, we can try using mathematical induction. If you want to use mathematical induction, you have to do two steps. The first one is the first step is a very simple step. It's called basis step. And in basis step, we just simply check that our statement holds for n equals 1. So I want to show the equality of these two expressions, 1 plus 2 plus all the way to n, and equals n times n plus 1 over 2. I want to show the equality of these two. So why don't I check that this is true for n equals 1? So for n equals 1, so let me say basis step, we will prove this formula using mathematical induction. So basis step for n equals 1. Well, the left-hand side will be just 1, and the right-hand side will be 1 times 1 plus 1 over 2, which means 1 equals 1. And this is, of course, true. What about the next step, which is called inductive step? So suppose, so in inductive step, as we explained, we have to assume that the statement holds for n equals k. So that will be my assumption. And I will show that it will be true for n equals k plus 1. So suppose that, so my assumption is that the statement, this statement holds for n equals k. So then that means suppose that 1 plus 2 plus k equals k times k plus 1 over 2. And we will show that it will be true for k plus 1. See this statement, if I want to show that it's true for k plus 1, that means I have to show that 1 plus all the way to k plus 1 equals k plus 1 times k plus 2 over 2. See, it's n times n plus 1 over 2. So if n is k plus 1, the right-hand side will become k plus 1 times k plus 2 over 2. So this is my assumption. So this part is my assumption. I am assuming that this is true and this equality holds. I want to show that this equality holds. So how can I connect? So you know that in mathematics, always whenever you have an assumption and you have a conclusion, your job is to try to connect the assumption with the conclusion, make a connection between them. But here, the connection is obvious. What is the connection between proving this equality and this equality? But when we look at this equality that we want to show, now if you look at the left-hand side, it says 1 plus all the way to k and then plus k plus 1. But then for the first k terms, 1 plus all the way to k, well, I know that I'm assuming that that's equal to k times k plus 1 over 2, right? The first k terms here, I am assuming that it's equal to k times k plus 1 over 2. So why don't I replace it with k times k plus 1 over 2? And then see what happens. So and we will show this. So now 1 plus 2 plus all the way to k plus k plus 1 is equal to k plus k times k plus 1 over 2 plus k plus 1. The first k terms by assumption is k times k plus 1 over 2. So this part here, we use the fact that 1 plus all the way to k is equal to k times k plus 1 over 2. Now, when I want to simplify this, I can take k plus 1 as a common factor. K plus 1, let's take it common factor. And then from the first term, k over 2 will be left. And from the second term, 1 will be left. Look at here, I have addition of 2 terms. And k plus 1 is a common factor. I took it out. And then from first term, k over 2 is left. From second term, 1 is left. And then this is same as k plus 1 times k plus 2 over 2. K over 2 plus 1 is same as, if you take 2 as common denominator, is same as k plus 2 over 2. And then this is k plus 1 times k plus 2 over 2. Which is what I needed to show. So we showed 1 plus k plus 1 equals k plus 1 times k plus 2 over 2 as desired. Therefore, we can say that 1 plus all the way to n is equal to n times n plus 1 over 2 by induction, or mathematical induction, or we can just say by induction. This is the formula I wanted to show, and we proved it by induction. The first completing basis step, which was a very easy step, just checking for n equals 1, just checking the formula that it holds for n equals 1. And then we assume that the formula holds for n equals k, and we showed that it holds for n equals k plus 1. Okay, now this mathematical induction method can be used, as we said, for proving any statement which depends on a natural number n. So now when we say statement, it could be proving an equality, like what we did here, or it could be other things, for example, proving inequalities, or proving a statement about divisibility of a number, or a statement about a set. So it doesn't have, my point is, it doesn't have to be an equality necessarily, as long as it's a statement in terms of n, where n is a natural number, you can try induction. So in your book, it gives examples of using induction for all types that I just said. For example, proving inequalities, equalities, facts about sets, and divisibility. So in each of these types, there could be thousands of examples, and we could have more types as well. So these are the types that are mentioned in your book. So let me also mention about these types and few examples of each type, and then you can do more examples of each type in exercises, of course. So maybe I can say a remark here that the remark is a mathematical induction can be used to prove any statement of the form P of n, and such statement can be of the form of an equality or inequality, or a statement about divisibility of numbers, or facts about sets, etc. So why did I mention these specific types? Because these specific types are the types that are mentioned in your book. But of course, we can have so many more types, as long as we have a statement that includes an integer n. It could be about matrices, for example, product of, for example, n matrices having a certain property, or let's say, for example, n by n matrices. You will see in linear algebra that the size of matrices, let's say square matrices, n by n, and n is an integer. So you can also use mathematical induction there, because again, as long as you have a statement that you want to show it's valid for a natural number n. But these specific types are mentioned in your book. So that's why I said we'll provide a few examples of each of these types. And more types you will see in other courses that you take in future. You will see other types of problems that you can use mathematical induction to prove them. So for, let's say, equality, for equalities, we already proved one equality, which was the very standard identity, 1 plus 2 all the way to n equals n times n plus 1 over 2. Now let's look at another example of that type. Example, a conjecture, a formula for the sum of first n positive odd integers, then prove your statement or prove your conjecture using mathematical induction. So in the previous example, we looked at the first n integers, n positive integers, the sum of first n positive integers, 1 plus 2 plus 3 all the way to plus n, and we saw that the result is n times n plus 1 over 2. Now we want to look at the sum of first n positive odd integers. So it says first make a conjecture. So conjecture means a guess, basically, in mathematics. If you want to make a guess about a specific result, we say conjecture. So to make a conjecture, to make a guess, you can try, first few examples or few numbers. Examples, we saw that, it's not a method of proof, but it's a good way to get some idea or make a conjecture. So why don't we look at few examples of this case that is asked from us, the sum of first n positive odd integers. So for example, the first odd integer is 1. And, well, 1 is 1. There's no sum here. But then if I look at the first two, so note, the first two odd integers, the sum of first two odd integers, 1 plus 3, that's 4, which is 2 squared, right? And then if I look at the first three odd integers and add them, 1 plus 3 plus 5, that's 4 plus 5, which is 9, and 9 is 3 squared. I look at the next case, the sum of first 4 positive odd integers, 1 plus 3 plus 5 plus 7. The first 4 positive odd integers, 1, 3, 5, and 7. If I add them, 4 plus 5 is 9, plus 7 is 16, and 16 is 4 squared, and so on. So the conjecture that we can make based on this pattern is that the sum of first n odd integers is n squared, right? The first two odd integers, the sum was 2 squared. First three odd integers, sum was 3 squared. And so on. The sum of first odd integers is n squared. Mathematically, we could write this as 1 plus 3 plus 5. The nth odd integer will be, so for example, the second odd integer is 3, which is 2 times 2 minus 1. Third odd integer is 5, which is 2 times 3 minus 1, and so on. The nth odd integer will be 2 times n minus 1, and the result is n squared. The sum of 1 plus 3 all the way to 2n minus 1 is equal to n squared. So let's prove it by induction. So proof by induction. So first we have to look at the basis step. Basis step means just check it simply for n equals 1. Then 2 times 1 minus 1 equals 1, which is same as 1 squared. So left-hand side and right-hand side, in this case, both will be 1, and therefore they will be equal. And then we have to look at inductive step. So suppose that 1 plus 2 all the way to 2k minus 1 is equal to k squared, which is also called induction hypothesis. Remember, in induction hypothesis, which is a part of induction in inductive step, we assume that the statement we want to show or we want to prove holds for n equals k. And then we show that it holds for n equals k plus 1. The statement that we want to show is this one. And we are assuming that it holds for n equals k, meaning that 1 plus 3 all the way to 2k minus 1 is equal to k squared. And we want to show that 1 plus 2 all the way to 2 times k plus 1 minus 1. See, if I replace this n here with k plus 1, I'll get 2 times k plus 1 minus 1. And I want to show that this is equal to k plus 1 the whole squared, i.e. now the left-hand side, if I expand it, 1 plus 2, the last number will be 2k plus 2 minus 1, which is 2k plus 1. And the one before that is 2k minus 1. So 2k minus 1, and then 2k plus 1. And then I want to show that this is k plus 1 the whole squared. Now note that if I start with the left-hand side, if I call this part left-hand side is equal to 1 plus 2. So not 1 plus 2, 1 plus 3, because we are looking at the odd integers. First, k odd integers. So the first one is 1, and then 3, all the way to 2k minus 1. Same thing here. And here. Okay. So 1 plus 3 plus 2k minus 1 plus 2k plus 1 is equal to, now this part here is k squared, right? By my assumption or induction hypothesis, we said 1 plus 3 all the way to 2k minus 1 is equal to k squared. So this is k squared by assumption or hypothesis. So the result will be equal to k squared plus 2k plus 1. And then this is, of course, k plus 1 the whole squared, which is what we needed to show. So we showed that 1 plus 3 all the way to 2k plus 1 is equal to k plus 1 the whole squared plus 1 plus 3 all the way to 2n minus 1 is equal to n squared as desired. Okay, let's look at some inequalities now. So example, use mathematical induction to prove that 2 to power n is less than n factorial for every n bigger than or equal to 4. Well, here it's a little bit different because we have a statement in terms of n, and n is a natural number, but we want to show that it's true for not every natural number, but for every natural number n bigger than or equal to 4. So this is not a big deal because, the idea in mathematical induction was that, we start from some basis where normally the basis is n equals 1. And then we also prove that if it's true for n equals k, then it will be true for n equals k plus 1. So if it's true for 1, then it will be true for 1 plus 1, which is 2. And then therefore it will be true for 2 plus 1, which is 3, and so on. But here we want to show that it's true for every n bigger than or equal to 4. So that means the only modification that we need is in our basis step. So in the basis step, instead of checking that the statement holds for n equals 1, here we will check that the statement holds for n equals 4, and the rest is same. We will assume it's true for n equals k. We will show it's true for n equals k plus 1. And because we already checked that it's true for n equals 4, that means it will be true for 4 plus 1, which is 5. And then once we know it's true for 5, then we can say it's true for 5 plus 1, which is 6, and so on. So maybe I can mention as a remark here that So to prove that a statement of the form P of n holds for, let's say, n bigger than or equal to C for some C in n. So again, first step, check that P of n holds for n equals C. Again, this is called basis step. To assume it holds for n equals k plus 1. Assume it holds for n equals k, and show it holds for n equals k plus 1, which is inductive step, as we said before. So it's still everything same as before. The only difference is that basis step. In basis step, instead of checking for n equals 1, we check for n equals c, if you want to show that everything holds for n bigger than or equal to c. So back to example above. We want to show that this statement holds for every n bigger than or equal to 4. So first we have to check for n equals 4. So basis step. N equals 4, then 2 to the power 4 is 16, which is less than 4 factorial. 4 factorial, as you know, means 1 times 2 times 3 times 4, and that's 24. So 16 is less than 24. Well, that's true. Now, inductive step. Suppose that 2 to the power k is less than k factorial, which, as we said, is called induction hypothesis. And we will show that the statement holds for n equals k plus 1, meaning that 2 to the power k plus 1 is less than k plus 1 factorial. Now, again, our job is to make a connection or create a connection between the assumption, which is 2 to the power k less than k factorial, and the conclusion, which is 2 to the power k plus 1 less than k plus 1 factorial. Well, this is almost obvious. 2 to the power k plus 1, of course, can be written as 2 to the power k times 2. And 2 to the power k, we already know that is less than k factorial. So note 2 to the power k plus 1 is equal to 2 times 2 to the power k. And that's less than 2 times k factorial. Because 2 to the power k is less than k factorial. And 2 is less than k plus 1. Right? Because remember, what do we know about k? K is, of course, or let's say less than equal to k plus 1. K is, of course, a natural number here. And k plus 1, therefore, so k is at least 1, and therefore k plus 1 is at least 2. And therefore, this is less than equal to k plus 1 times k factorial. But k plus 1 times k factorial means k plus 1 factorial. K plus 1 factorial means 1 times 2 times all the way to k plus 1, which is 1 times 2 times all the way to k, which is k factorial, then times k plus 1. So we showed 2 to the power k plus 1 is less than k plus 1 factorial as desired. So here you may tell me that, well, here we have less than equal. Why do we still have less than here? Strict inequality. Well, the answer is, according to properties of inequalities, if let's say you have three numbers, for example, A is less than B and B is less than equal to C, then I can say A is less than C. Right? If A is less than B and B is less than equal to C, then A is less than C. So I can say this number is less than this number. All right. Now, for example, another example for divisibility. Example, let n be a natural number. Show that n cubed minus n is divisible by 3. N cubed minus n is divisible by 3. So how can we show this using induction? So solution 1, using induction. Again, we have a basis step, which means we have to check it for n equals 1. Then 1 cubed minus 1 is 0. And of course, 3 divides 0. 0 is divisible by any number except 0 itself. And then inductive step. Suppose that 3 divides k squared, k cubed minus k. Right, in inductive step, I have to assume that my statement holds for n equals k. So that means k cubed minus k is divisible by 3, which is what I wrote. And we want to show that 3 divides, the statement holds for k plus 1. So k plus 1 means k plus 1 cubed. 3 divides k plus 1 cubed minus k plus 1. Now, what does that mean if I simplify a little bit, just a little bit algebra? 3 divides, now if I expand that, that's k cubed plus 3k squared plus 3k plus 1 minus k plus 1. And 1 cancels with 1, so 3 divides k cubed minus k. Just again, take this term along with this term together. 1 minus 1, they cancel. 1 minus 1 is 0. And then plus 3k squared plus 3k. So now note that first of all, 3 divides k cubed minus k by assumption. Also, 3 divides 3 times k squared plus k, which is same as 3k squared plus 3k, right? This is obvious, right? 3 divides 3 times a number. 3 times a number is a multiple of 3, obviously, which means 3 divides this number. When you say 3 divides a number, it means that number is a multiple of 3. So 3 divides this number and 3 divides this number. So if 3 divides this number and 3 divides this number, then I can say 3 divides the addition of those two numbers. So this is a property that we saw in chapter 4, that if, let's say, m divides a and then m divides b, then m, of course, divides the addition of a and b as well. So M divides A, M divides B. Divide M divides A plus B. So that means 3 divides K cubed minus K plus 3 times 3K squared plus 3K. Right? 3 divides this guy plus this guy, but that guy plus that guy was same as K plus 1 cubed minus K plus 1. That's what we showed previously. So that means 3 divides K plus 1 cubed minus K plus 1. So that's one solution. Solution 2, you can use division algorithm. So case 1, we know that by division algorithm, the remainder of any number n when divided by 3 is either 0 or 1 or 2. So case 1, if the remainder is 0, meaning that if n is a multiple of 3, then n cubed minus n. I want to show, remember the question? We wanted to show n cubed minus n is divisible by 3. So I have only 3 possibilities for n. Either the remainder of n divided by 3 is 0, or it's 1, or it's 2. So I will consider 3 cases. And in each of these 3 cases, I will show that n cubed minus n is a number divisible by 3. In this case, it's very easy. If n is 3k, then n cubed minus a will be 3k cubed minus 3k. And that's 27k cubed minus 3k, and that's 3 times 9k cubed minus k. So 3 times a number, that means 3 divides n cubed minus n. Case 2, if the remainder is 1, I can also say for some integer k, or here you could also say for some integer k, then n cubed minus n will be 3k plus 1 cubed minus 3k plus 1. So if you expand this, 27k cubed plus 27k squared plus 9k plus 1 minus 3k plus 1. And then this is same as 27k cubed plus 27k squared plus 6k. And then I can write this 3 times a number. So 3 times 9k cubed plus 9k squared plus 2k. And therefore, it's a multiple of 3. And case 3, if n equals 3k plus 2, or in some integer k, exercise show that 3 divides n cubed minus n. In this case as well. And therefore, in each case, n cubed minus n will be divisible by 3, and the number will be divisible by 3. So this is a method not using induction. We use division algorithm in solution 2. But in solution 1, we didn't use in division algorithm. Instead, we used induction, meaning that we checked for n equals 1, then we assumed it's true for n equals k, and we proved that it's true for n equals k plus 1. Okay, so this is an example for divisibility case, and also facts about sets. So example, show that a set with n elements, n bigger than equal to 1, with n bigger than equal to 1, has 2 to the power n subsets. Now again, proof by induction. Proof by induction. So n equals 1. It's very easy to verify. Basic step. N equals 1. A set with one element, because we want to show that a set with n elements has 2 to the power n subsets. So a set with one element, i.e. a set of the form, let's say A, has 2 to the power 1 equals 2 subsets, namely, so a set of this form has exactly 2 subsets. What are the subsets of a set of this form? Empty set, which is the subset of every set, and also the set A itself. There is nothing else, right? So it has 2 subsets, and 2 means 2 to the power 1. Therefore, in this case, if n equals 1, the statement has been proved. Because a set with n elements, we wanted to show that it has 2 to the power n subsets. And then we have to do inductive step. Suppose that a set, that every set basically, every set with k elements has 2 to the power k subsets. And we want to show every set with k plus 1 elements has 2 to the power k plus 1 subsets. So consider a set, an arbitrary set with k plus 1 elements. Say, let's say A equals A1 to AK, and then AK plus 1. Remember, when we provide the proof has to be in general. So when you want to show that a set with k plus 1 elements has 2 to the power k plus 1 subsets, now we are allowed to choose a notation for our set with k plus 1 elements, but the notation has to be a notation that is given in general for an arbitrary set, not a specific one. So an arbitrary set with k plus 1 elements is of the form A1, A2 to AK to AK plus 1. So it's a general notation, arbitrary set. I'm not providing any specific example, right? So we have a set, arbitrary set with k plus 1 elements. And I know that if it had k elements, then I know how many subsets it would have. But right now it has k plus 1 elements. Now, how can I make a connection between a set with k plus 1 elements and a set with k elements? Again, remember the our job is to make a connection between the assumption, which is the statement being true for n equals k, and the conclusion, which is the statement being true for n equals k plus 1. So what is the connection? This set with k plus 1 elements, we can write it as, so note A, we can write it as A1 to AK, and then union AK plus 1. Right? Now, when I consider a subset of A, what can I say about an arbitrary subset of A? So a subset of A is either a subset of the first set A1 to AK, right? So now any subset of A is either a subset of A1 to AK if it does not include AK plus 1. So any subset of A either doesn't have AK plus 1, in that case it will be a subset of this guy here, or it has AK plus 1. If it has AK plus 1, once I remove AK plus 1 from that set, again, I'll get a subset of A1 to AK, right? So, or is either a subset of this, or is a subset of A1 to AK union AK plus 1. Because if it has AK plus 1, if it doesn't have AK plus 1, then it's a subset of A1 to AK. If it has AK plus 1, once I remove it, it will become a subset of A1 to AK, which means in that case, the subset of A will be a subset of A1 to AK union AK plus 1 itself. So what can I say about the set of all subsets of A? As the set of all subsets of A will be the set of all elements or all subsets, let's say X, such that X is a subset of A1 to AK, union all subsets of the form, let's say X union AK plus 1, where again X is a subset of A1 to AK. Any subset of A is either a subset of A1 to AK, or it's a subset of A1 to AK union AK plus 1, in the case that the subset includes AK plus 1. And this is in the case that the subset does not include AK plus 1. So then that means the number of subsets of A equals number of subsets of A1 to AK plus number of subsets of A1 to AK. See, number of elements of this set is number of elements of this set, which is number of subsets of A1 to AK plus AK, plus number of elements of this set, because these two sets have no intersection, right? So number of elements in A union B is number of elements in A plus number of elements in B. Now, number of elements in B is how much? How many elements do we have in this set? The number of elements in this set is same as the number of options that I have for X, right? Because for every option that I have for X, then I have one set and exactly one set of the form X union AK plus one. So this part is fixed. What is changing here? X is changing. So number of elements that I have in this set is the number of options that I have for X. Because X is changing, the second part is fixed. And number of options for X, X is subset of A1 to AK, means plus number of subsets of A1 to AK. I also mentioned here that number of sets of the form X union AK, same as number of sets of the form X. Because form X has X union AK plus 1, as AK plus 1 is fixed. Well, what does that mean then? That means number of subsets of A is how much? Number of subsets of this plus itself. So these two terms are exactly the same. You can see it here, which means 2 times this term. So 2 times number of subsets of A1 to AK. And by assumption, this is 2 times 2 to the power K, and that's 2 to the power K plus 1. So that's it. So we showed any set with K plus 1 elements as 2 to the power K plus 1 subsets. And that's exactly what we needed to show. And one exercise that you can do again for in the topic of facts about sets is to show De Morgan's law for n sets. Says or generalization of De Morgan's law. Generalization. Say prove the following. Generalization of De Morgan's law, which says intersection of a j from 1 to n bar is same as union of a j bar, j from 1 to n, where A1 to AN are subsets of a universal set U, and N is bigger than or equal to 2. So again, you want to prove a statement that depends on N, and N is a positive integer. You want to show that the statement holds for every N bigger than or equal to 2. So as we said before, as a remark, the only difference will be that for basis step, you have to check the statement for N equals 2, and then you assume that it holds for N equals K, and you will prove it for N equals K plus 1. And then that will mean that this identity, which is a generalization of De Morgan's law, will hold for every N bigger than or equal to 2. Okay, guys, so these are some examples of different types of topics where induction could be used. There are more topics, as I said before. But yeah, so the only key here is to do lots of exercise and practice to get comfortable about how you do the inductive step, because basis step is easy, but inductive step, how can you go from induction hypothesis, which says the statement holds for N equals K, to go from there to show, that the statement holds for N equals K plus 1. How can you make the connection between the assumption and conclusion in this case? So please do lots of practice. I'll also upload some questions in the exercise and next assignment. Okay, so thank you and see you Thursday.